Robots increasingly rely on data-intensive learning. But how do we scale that data, especially in realistic, task-relevant environments? Simulation offers a scalable and safe way to train and evaluate robots. But there's a catch. We need large numbers of realistic, diverse, and task-relevant scenes. Manually designing them doesn't scale. We tackle this challenge with a two-step strategy. First, pre-train on broad procedural data. Then, steer generation toward downstream goals. To support pre-training, we introduce a dataset of over 44 million SE3 scenes, spanning 5 distinct scene types. Using diffusion, we generate scenes represented as unordered object sets, where each object has a continuous pose and a discrete asset ID from a fixed library. Our models learn to decide on the number of objects, the object types, and the SE3 object poses. But why distill procedural data into a generative model? It gives us a unified, differentiable prior that can be steered toward downstream goals. We study 3 strategies for model steering. First, we adopt reinforcement learning-based post-training for scene generative models. We demonstrate post-training using an object count reward and show that the model can be steered to generate scenes well beyond the pre-training distribution. Second, we explore conditional generation. We study text condition training, allowing us to ask for scenes satisfying object counts, object names, or spatial object arrangements. We also explore test time in painting, directly in the structured scene representation. Examples are scene rearrangement, where we regenerate the poses of existing objects, and scene completion, where we synthesize new values for empty object slots. Third, we introduce a novel Inference-Time Monte Carlo tree search strategy over partial scenes that enables optimizing task rewards without further training. We incrementally construct a scene through partial in-painting, where at each tree search step, an in-painting mask identifies which objects to regenerate, such as unstable ones, or empty slots, and the reward function evaluates the resulting scene. Following generation, we apply a lightweight post-processing step to ensure physical feasibility. We validate simulation readiness by teleoperating a mobile KUKA EVA robot to interact with our generated scenes without requiring any manual scene correction. Our framework enables scalable generation of task-relevant simulation environments for robotic manipulation. Please check out our paper and website to learn more.